So now our next speaker is Harry Bhadeshia. Harry's a very long-standing fellow of the college. He joined Darwin as a graduate student in 1976, did his PhD, and in 1981 became a fellow. So he's well up in the seniority list of fellows. He's the Tata Steel Professor of Metallurgy here in the university and director of the SKF University Technology Centre. Now, Harry's research in metallurgy has included work on the steel for the rails in the Channel Tunnel and projects to do also with the Ministry of Defence. His honours are numerous. He's a Fellow of the Royal Society, Fellow of the Royal Academy of Engineering, and the Institute of Materials, Mineral and Mining has awarded him their Bessemer Gold Medal. So we're in very good hands. Harry is going to talk on the first bulk nanostructured metal. So, Harry.
So, today is one of the rare occasions when I wore a tie, okay? And the rest of the people did not, so I've dressed down for this lecture. Now, I'm going to begin with a question. Can anybody tell me what this is? Well, crystals, right? Everyone recognizes crystals. I took this picture at the Raman Institute in Bangalore, where there are fluorescing crystals. They look beautiful, and that's what an ordinary person would recognize as a crystal. But equally beautiful is the crystals that we make in engineering. So here, for example, is a single crystal, which is a turbine blade that goes into an aircraft engine. So there are thousands of these grown by Rolls-Royce annually to put in aircraft engines, because if we have boundaries between crystals, there are defects, and atoms can diffuse rapidly between those boundaries. And these things serve at temperatures of about 1400 degrees C, rotating very, very fast. So they get longer if diffusion happens. So if you make them as single crystals, then they are very strong at high temperatures. But the vast majority of metallic materials are not single crystals. They are what we call polycrystals. That means we pack crystals together, and the dark lines that you see between the crystals are boundaries, grain boundaries. And the closer spaced those boundaries are, the stronger your material becomes. So if you want to make strong materials, you've got to pack a very large density of interfaces per unit volume of material. That means make the crystals as fine as possible. The strength is not the only parameter when you want to make something useful. You need, any fool can design a steel which is incredibly strong. But to give it the property which makes the steel safe to use, for example, toughness, that means if you have an impact, there's no fracture, the energy is absorbed. So just recently, last week, I was traveling to Poland by taxi to Luton Airport, and a car hit from the side at a high speed. So both the cars are written off, but absolutely no one was injured, because the car is designed to absorb the energy of impact, and the passenger compartment remains intact, but the cars are destroyed in the process. Yeah? You would not make a car out of window glass. Window glass is extremely strong, but it doesn't have the ability to absorb energy when it breaks. Okay? So the great thing about having lots and lots of crystals inside your material is that it makes the material strong, and it makes it tough as well. That means it can absorb energy on impact. And what I'm going to talk today, the subject of my talk today, is about nanocrystalline metal. So over the last 30 years, there's been hundreds of millions of pounds spent on trying to make the crystals as fine as possible, mostly without success. And then there was a breakthrough, which I'm going to describe today. Now, I'll start with this problem. How do you actually design a bulk nanocrystalline steel, which is very strong, tough, and cheap? Okay? This is the kind of statement you put in research proposals, that I'm going to do it, okay? So I want to put a bit more substance onto this. What do we mean by bulk? I don't mean a very small object created in the laboratory by very severe processing. This is a picture that I took in the oil sands mines in Canada. And just to illustrate to you the scale of that truck, that's me over there, one tire. Okay, so I want to be able to make objects which are very big, are very strong, and they can be big in all three dimensions. That means you cannot have very, very rapid treatments, processing, very rapid cooling or very severe deformation. Now, what do we mean by nanocrystalline? Nano means 10 to the power of -9, and I'll illustrate that later on. Andy was talking about big numbers. I'm talking about incredibly small numbers, 10 to the -9 of a meter. But to give you an idea of scale, most of you must have heard about nanotubes, right? So carbon nanotubes have had a lot of publicity, and whatever we do, we've got to beat those nanotubes, yeah? Because as the bursar said, you know, this is not just steel, it's Marks and Spencer steel, okay? And what do we mean by cheap? Any idea? Well, I'll put this into context. A lot of you will buy bottled water, okay? And there's absolutely no purpose to that. The tap water is perfectly okay, yet you buy it in a plastic bottle which has been transported from a spring in Scotland and use it. So you're prepared to spend £1 on a bottle, a liter of water or less. So we need to make the material as cheap as that, because that is regarded as cheap. So I'm going to go through how people have attempted to do this, but in order to give you an idea of what strength means, I borrowed an apple from the kitchen, and it turns out that the weight of an apple is a Newton. Yeah, it is almost a Newton. If I put this apple on 1 square meter, then that's a Pascal. That's a unit of stress. So I'm going to talk about a material which can support the weight of 2.5 billion apples on 1 square meter, assuming that we don't end up with the juice, okay? So back in 1956, we could actually make iron with a strength of 10 gigapascal. That means 10 billion apples on 1 square meter. But look at the size scale there. We are talking about a particle of iron which is about 5 millionths of a meter in size. And you can see that the strength collapses as soon as I scale that up to a larger size of 20 millionths of a micrometer. And that's because when you make something very small, the chances of getting a defect in there are very, very small. And that's why, you know, if you take a glass rod, you can't bend it, it will shatter. But if you take a glass fiber, you can do that without shattering it, because the chances of finding a defect are much smaller. So we knew this back in 1956, that if you try to make things perfect, then there will be a problem as soon as you scale it up. This, on the other hand, is something that we worked on about 20 years ago, where we made steel which is commercial and can support the weight of 5.5 billion apples on 1 square meter. And it is so ductile. Ductile means it deforms before breaking, absorbing energy. You can tie a knot with it. You can't tie a knot with carbon fiber. So it seemed like we already had a very strong material, and the reason why it is strong is this picture shows individual atoms. We have equipment where you can see individual atoms, and each dot is a single atom. And you see these dark regions here, those are the boundaries between the crystals. So the crystals have become so fine because the material is produced by taking, let's say, 50 grams of material and stretching it out into 2 kilometers. That's a huge amount of deformation. And that introduces huge numbers of defects, and in this case, the defects strengthen the material. Okay? When you do that, you lose the size sensitivity. So this is the first slide that I showed, where the strength collapses when you take a perfect crystal and you make it bigger. Here we are getting strengthening by introducing defects, and therefore there's no longer the size sensitivity. Now the problem with this is that if you stretch this out to 2 kilometers, you are going to end up with incredibly fine material, and here it is. I'll pass it around. This is 5.5 gigapascals strong, but you can see it's incredibly fine. And just to give you an idea of how fine it is, the denier is the unit of thread, and men's socks are approximately 50 deniers, and women's stockings are about 10 denier. And this particular wire is 9 denier. So in principle, you could make stockings out of this steel wire. So we are not going to be able to make bridges or trucks, etc., out of this material. Now, carbon nanotubes have had huge publicity. You could read the Daily Telegraph and they would say, engineers are salivating over the properties of carbon nanotubes because, look, the strength is 130 gigapascals. It's the stuff of which dreams are made of. And there's another property called the modulus, which is the stiffness of the material. And along the axis of that tube, the stiffness is 6 times greater than that of steel. So we have lunchtime talks in Darwin where students make presentations. And there was one particular student who made a presentation about a story from NASA where they invested $17 million into making a space elevator. Okay? This is an old Russian idea. The problem is that if you make a rope for the elevator, it's not able to support its own weight when you get to 120,000 kilometers, which is how long it would be. And I had a very hard time convincing him over a period of 4 hours that this is not a viable idea because these properties are only there for very, very small scales. As soon as you scale it up, elementary thermodynamics tells you that there is a cost to creating a defect, but when you introduce a defect, it also changes the number of ways in which you can arrange the atoms, and that's called configurational entropy, and that favors the formation of a defect. So if you balance these two terms, you get a concentration of defects inside anything that you make, which is equilibrium. That means there's nothing you can do to get rid of them. They will always be there. If I increase the number of atoms in my sample, the number of defects will increase, and that is why the strength collapses. And there's no carbon nanotube rope greater than 2 millimeters, let alone 120,000 kilometers, which can beat steel. So I wrote a paper. This was inspired by this discussion in Darwin from one of the lunchtime talks, and I sent it to NASA. So no one any longer talks about space elevators. Okay. The other problem with very strong materials is that, of course, if you load the carbon nanotube to 130 gigapascals, then the amount of energy stored in it is more than dynamite. And because its stiffness is bigger than dynamite, the velocity of the explosion, and Chris might talk about that, is much, much greater. Yeah, so this would not be a safe engineering structure. It's like when you get whiplash when a chain which is pulling a heavy load breaks. So nanotubes are not the answer. And just to summarize, strength which is produced by deformation, you are limited to the form of the material, whether it's wires or whether it's thin sheets. And when you rely on perfection, the problem is doomed as soon as you increase the size of your object. Now, back in the 1960s, there was a major, major discovery in Britain, which really should have won a Nobel Prize because it has influenced all your lives. Okay? And that is a process called thermo-mechanical processing. So if you go to a steel plant, they can produce hundreds of millions of tons of material in which the crystals are extremely fine, of the order of 1/1,000,000th of a micrometer. And that made steels incredibly reliable. So what do we mean by reliable? Well, there might be computer scientists here, but you know that software and computer systems are totally unreliable. They need to treat these like engineers treat machines. You would never make, an engineering object which needs updates every 2 or 3 days. This material is now in service, and there are approximately 40 billion tons of it around you. Okay? You don't notice it at all because it's totally, not totally, but almost completely reliable. It doesn't fail you, so you don't need to worry about it. Okay? Now, in order to create fine crystals, there is a cost, and that cost is an energy per unit area of the boundary. And the boundaries are created by doing something to the material, so you're providing that energy. So if you balance those two, you can work out the smallest crystal size that you could get using thermo-mechanical processing. And a simple calculation tells us that we could actually get to very, very small grain sizes. But when you look at the very large number of experiments and industrial experiments that have been done, we are not actually reaching 1/1,000,000th of a micrometer, in spite of what theory tells you. And the reason is, if you undercool the steel before these crystals are created, then there will be heat released. This is, it's just like when you add some salt to water, sometimes the water heats up. That's called an enthalpy change. So it heats up, and therefore the crystals become bigger. And when we take account of that recoalescence, we are not going to reach much less than 1/1,000,000th of a micrometer. What we are aiming for is 1/10⁹ of a meter. So thermomechanical processing has been incredibly successful. There are 40 billion tons of this material in service, but it's limited by this process of internal heat generation. So we're not going to get to a fine structure. So to summarize, what we need is, when we create very fine crystals, we need to store the heat inside the material. And of course, if we reduce the rate at which the crystals form, then the heat has a chance to escape. And it's always true that if we transform at a low temperature, we will get finer and finer crystals. There is one more difficulty. When you take a piece of metal and you bend it, the first time you bend it, it's easy. But if you try to unbend it, it's much more difficult. That's called work hardening. So the material actually becomes harder when you deform it. And that's a very good thing, because supposing I get a small defect here, the work hardening will strengthen that defect, and therefore you can get lots of elongation before fracture. Okay? So work hardening is an essential property. If you don't have it, you get a plastic instability immediately, and you lose your ductility. So we need a mechanism of work hardening in addition to all those requirements. Okay, so that brings me to today's talk. And a crystal basically involves an ordered arrangement of atoms, and there are many structures in which the atoms can order for iron. So this is the most common on Earth. We call it a body-centered cubic unit cell, where we have an atom of iron in the middle and atoms at the corners. And this is what happens at higher temperatures. It's called austenite, which has atoms at the centers of the faces and at the corners. And right in the center of the Earth, where there is a huge pressure and temperature, we have this hexagonal form of iron, which we can create on the surface by adding certain things to the steel. But today I'm going to focus on just these two. At high temperatures, we have this arrangement of iron atoms. At low temperatures, it becomes this. And really, by controlling these transformations and the mechanism by which this pattern changes is how we design steels. So one mechanism is you do not break any of the bonds, right? But you change the pattern by a physical deformation. So that's so we have a particular arrangement there, and a deformation which is driven by temperature or by other means changes the pattern. And just to show you that this is a real thing, here's another movie, and about halfway through, you'll see a remarkable change happening. Okay? So we are looking at the surface of the high temperature phase. Okay, so these are crystals of the high temperature, and you can see we are generating crystals automatically causing deformations. Yeah, the deformation is driven by the change in temperature. So it's a real physical effect, and this is the basis of also shape memory alloys, which you might have heard of, where you can, if I reverse the temperature, the shape goes back to the original shape. Now, these are very large deformations. Okay, so there's a shear strain of about 0.26. That compares with a typical elastic strain, which is 0.001. So in order to minimize the strain energy, the crystals form as thin plates, which is very good because we want them to be as thin as possible. That's a fine crystal. And the elastic strain energy, this is happening inside the bulk of material, so these crystals are pushing against each other, effectively reduces the heat that is released when the transformation happens. Okay? So you're storing the energy inside the material rather than releasing it as heat. And this slide summarizes about 30 years of research on a particular kind of crystal, which is called Bainite, which forms by the mechanism that I illustrated with absolutely no diffusion of any atoms. However, carbon is a very small atom compared with iron, and it's able to move about much more rapidly than iron. So it doesn't like to be inside that body-centered cubic phase. It wants to get out and go into the parent phase. Within about a quarter of a second, the carbon escapes from here into the surrounding, and sometimes it precipitates as a brittle phase called cementite, which is an iron carbide. We can stop this reaction here by adding certain elements. So by doing that, we end up with a mixture of the parent phase and the product phase. And the parent phase is very good for absorbing energy and for providing work hardening. So this is basically an ideal structure. We are getting fine plates, we are retaining some of the parent phase, adding work hardening capacity. And this is what it really looks like. The scale here is a millionth of a meter. These are fine plates, and in between we have this retained parent phase. And this is not nanostructured because this is only a millionth of a meter, the scale. But this was the material which forms the basis of the rails that Mary described. So if you look at this material, there's a process known as rolling contact fatigue. That means whenever a wheel goes over the surface of a rail, you induce stresses underneath, and eventually that bit flakes off, and then you have a problem. Okay? And this material simply doesn't show any rolling contact fatigue compared with normal rails. And it's the only material which also reduces wear rate on the wheel itself. Okay? So it's now in service in the Channel Tunnel and in various other places. So remember me next time you travel to France via Eurotunnel. But the strength level here is not as high as we want. Now, I said to you that we want to create fine crystals, and to create even finer crystals, we need to form them at a low temperature, okay? Bearing in mind that steel melts at about 1560 degrees centigrade, a low temperature would be, conventionally, would be about 400 degrees centigrade. But we wanted to find out whether there's a theoretical limit to the temperature at which we can form these crystals. And there is one further problem, is that if you cool to an even lower temperature, you get a very brittle crystal forming called martensite. So what we want is a steel where a gap is maintained between the good stuff and the bad stuff. And what we discovered from theory is that there is no limit to the lower temperature. We could go down to room temperature and form these crystals, let them grow inside the steel. But the problem is, if I actually form the crystals at room temperature, it will take me about 100 years. Yeah? So that's like wine. You make the steel, you store it, and then you sell it in 100 years. But I couldn't convince any of the industrial partners to take that up. So we went for another option, which is at a temperature at which pizza is cooked. So do you know what that temperature is? 200 degrees centigrade. Very good, excellent. You see? Perfect, 10 out of 10. Okay. So this is extraordinary because there is no other material which is cooked at a temperature of 200 degrees centigrade. It takes 10 days to generate this set of crystals. So basically, you put it into an oven and leave it there for 10 days. And this is the structure that you obtain. And if you showed this to a metallurgist, this is 40 millionth of a micrometer, so there's nothing exciting about it. But I want you to see that it's isotropic in all directions. Yeah? We're not creating an isotropic because the next image that I'm going to show you is at a much, much higher magnification. And it's absolutely breathtaking. Yeah? So are you ready? Okay. This is what we obtained. This is in a transmission electron microscope. The colors are, of course, false. You have parent phase, and these are actually finer than carbon nanotubes. Okay? So by transforming at this low temperature and maintaining all the other properties, we produced crystals inside solid steel which are finer than carbon nanotubes. And there is no limit to the dimensions of the material because this is just a heat treatment. It is now mass produced. This is an armor that we have produced. It's the best armor in the world. Yeah, here it is. It has been fired at many times with terrifying threats and has survived. It is a bit heavy, and I'm the safety officer, so I won't pass it around. But this is commercial. Okay? And the graph over there shows you that its ballistic performance is better than anything that exists, and it can take multiple shots. This cannot take multiple shots. So you can buy this now. It's commercially available, and it's also being used to protect ATM machines from people who want to blow them up and then take them away. Right. This is a section of an aircraft engine, and notice that this part is much bigger than this part. This is where all the action happens, the high temperature activity. This basically sucks the air. It's driven by the activity over here. And the big advantage is that the air, 70% of the air doesn't actually go through the engine. It shields the engine from noise, okay, and provides the thrust. And we would like this to be even bigger in dimension. So once I took a picture of a truck next to an aircraft engine, and airport security came to me and asked, why are you taking this picture? So I said, why isn't there a sign saying I can't take a picture? And then they went away. So if you make this bigger, then you need a material here which is much, much stronger than the current steels that are used. Okay? The torque becomes very large, and the shaft has to be able to bend. So if one of these blades breaks, the momentum is like 10 mini cars. Okay? So the engine undergoes severe vibration, but if the shaft is able to bend, then it accommodates that vibration temporarily, and then you can safely shut down the engine. So you cannot just have a strong material, but it's got to be also tough. And this nanostructured material that I showed you has those properties. So we are working with Rolls-Royce. This is actual shaft material being heat treated in Germany. This is around 1,000 degrees centigrade parent phase, and then you transfer it. Then you transfer it into a bath which is at 200 degrees centigrade, molten salt bath, and then you leave it there for 10 days. Okay? So this will more than likely be in aircraft engines approximately 10 years from now, because before you put something into an aircraft engine, you've got to be absolutely sure. So there will be test engines and so forth and so on. Now, just to illustrate to you how beautiful steel is, there is another activity that we are working on, which is bearings. Okay? And this is a small bearing. The bearing that goes into a windmill weighs 3.5 tons and is about 4 meters across. Okay? And I just want you to feel the pain involved. Okay? Again, I won't pass this around because it's quite heavy. Right, so imagine a simple bearing. Every time a ball goes across a point on the surface of the raceway, there's a pressure of 2 gigapascals, 2 billion apples on 1 square meter, felt under the surface of the raceway. And an aircraft bearing is going around at 25,000 revolutions per minute. And let's assume there are just 20 balls. Then the stress pulses per minute is 500,000 of those stress pulses. So just imagine that somebody punched you on the face 500,000 times per minute with a stress of 2 gigapascals. Yeah? So these materials have to be incredibly resilient and last for a very long time. So we are also working on using this nanostructured material for bearings. And that's where SKF in Sweden has invested a lot in Cambridge to take this forward, because there are many other properties that you need in order to satisfy all the requirements. Now, I said to you that it takes 100 years for the material to transform at room temperature and create even finer crystals, perhaps. Okay? So back in 2004, we made the material which would transform at room temperature. And there's a sample which is polished perfectly flat in the Science Museum and in my office. In the Science Museum, the temperature is controlled very accurately. In my office, it fluctuates a lot. So maybe you can do some comparisons. But the experiment, unfortunately, will be finished in 2104. So obviously, I'm not going to be around. But what you have to do is you have to tell this story to your children and your grandchildren. Okay? Otherwise, my ghost will come and haunt you. And that's the end of my talk, I think. Okay.